evening, boys and girls. Welcome to another lesson on Technical Sciences Grade 12. It is the 9th of October. It's a beautiful Friday. The weather is nice. It's not cold. It's not too hot. It is just nice and chilled. And I hope that you really had a great day at school and you are ready to learn some more with me on this topic, which is electric circuits. Remember, my dear learners, this topic, you can actually collect all the marks. You just need practice and practice and practice. And this is essentially what we have been doing throughout the week. We are looking at the different aspects of this topic, and we want to make sure that we are 100% certain that we can answer all the questions on this section. And that is why even today we will be looking at more and more questions on electric circuits so that we can concretize our knowledge of the theoretical part of this particular section and be able to answer any question that they ask us. And that is why we also use previous examination papers so that we get used to the standard of the question papers. So let us quickly look at the outline of the lesson today. In our overview, quickly just to revert back into what we are required to know as per the examination guidelines. And this I have done repeatedly for you, my dear learners, simply because there are new learners that are joining us, and we need to bring them to board in terms of what they are required to know on this particular topic. Furthermore, in the features of the topic, we will be learning electric circuits. And when we learn electric circuits, we will be using examples from previous question papers where we answer those questions. And that's how we are going to learn this particular topic. And then, furthermore, I will be giving you more tips into how to prepare for this particular examination. Right, this section of the work in an exam. Then, if we just look at the examination guidelines, remember, we must be able to state Ohm's law in words. And we know that by now, the potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. And then we must be able to determine the relationship between current, voltage, as well as resistance when the temperature is constant. So what happens to the current if the voltage is increased or the voltage is decreased, and so on. And we must know the difference between ohmic and non-ohmic conductors and give examples of each. We talked about that yesterday. And we must be able to solve problems using that equation. R is equal to V over I for series and parallel circuits. And we stick to a maximum of 4 resistors. Again, my dear learners, remember we must be able to use series and parallel resistors connection in circuits in combination with Ohm's law to answer any question that is given to us and to perform calculations, as well as application questions. And then a definition that we must know as well is to define the term EMF, the electromotive force. We know it is the potential difference across a cell when the circuit is open. And the other definition that we must know is the definition of internal resistance. And we know it is the resistance inside the cell when current flows through it. So I'm quickly going through those ones, my dear learners, because we've really talked about this before. Then we must be able to define power. And in terms of electric circuit, we say it is the rate at which electrical energy is converted in an electric circuit. And what I said to you, my dear learners, is Let us just stick to one definition for power. And we say power is the rate at which work is done. This definition, it still talks about the rate at which work is done or energy is converted. So it's still the same definition basically. It's just that this definition of power here is in terms of electrical energy. So we stick to one so that you don't get confused, and we say power is the rate at which work is done. We remember the SI unit for power, it's a watt. The practical unit of power, it's kilowatt hour. That is the one that we talked about when we talked about the cost of electricity yesterday. And then we must be able to calculate power using the following formulae. Power is equal to W divided by delta T, or power is equal to V times I, or power is equal to I squared times R, or power is equal to V squared over R. And we know what each variable means there. W we know is the energy, the V is the voltage, the potential difference, the I is the current, the R is the resistance. The delta T there refers to the time. And we talked about what a kilowatt hour is. And we know when you talk about a kilowatt hour, we basically refer to using 1 kilowatt of electricity for a period of 1 hour. And calculating the cost of electricity usage, when we know the power specifications of the appliances that we use and the duration in which we are using those appliances, if we know how much 1 kilowatt hour costs, and then the heat produced by the resistor in a circuit is given by that formula. W is equal to I squared multiplied by R multiplied by delta T. So that's essentially what we must know. So the only thing that we are really left with, my dear learners, is to look at how to calculate that particular heat, which is the energy that is dissipated. So that is all in terms of examination guidelines. We quickly move to our question. Right, it reads as follows. You are required to define the term power. And simply stated, my dear learners, we talked about this. I told you we simply stick to power is the rate at which work is done. Altogether, we don't have to define it in terms of electrical energy. So power is the rate at which work is done. Right, we know this. Power is the rate at which work is done. And for that, my dear learners, I am going to get 2 marks altogether. No part marking. All the keywords must be there and they must be in the correct context. It means they must be used correctly. We mustn't have a change in the scientific meaning. And you remember power is the rate altogether, rate at which work is done. Then we are given a scenario here. A circuit consists of a battery of 4 cells connected in series, each with an EMF of 3 volts. So let us just analyze that. So it is made up of 4 cells. I can see that it's 1 is the first cell, the second cell, the third cell, the fourth cell, positive and negative. Negative, positive, that's 1 cell. Another cell there, another cell there, another cell there. So we have 4 cells. And they are telling us that each has an EMF of 3 volts. In other words, this is 3 volts plus another 3 volts plus another 3 volts plus another 3 volts. In other words, when these cells are connected to each other and each is giving me 3 volts, then it tells me that they are going to give me 12 volts. The battery is then connected to 2 external resistors of 5 ohm and 2 ohm connected in parallel. Definitely we can see they are connected in parallel because the current divides altogether. And then the 2 resistors, meaning those in parallel, are connected in series with the third resistor of 2 ohms. So that resistor is connected in series. Why do we know it's connected in series? Because it receives the total current. Now we are required to calculate the total resistance of the circuit. Now you can actually say to me that, okay, Menir, let us first check. I said we must always track our electric current, our electricity, our electrons, our negative charges. There's our current. It goes all the way. Now there is no resistance in the conductor, so they are still having the 12 volts altogether. When we get here, the current divides. When the current divides, some of the current goes in that 5 ohm through the 5 ohm resistor, the other one goes into the 2 ohm resistor. So there are 2 pathways. So the total current divided at that point, and some of it will flow through there, some of it will flow through there. And then the current will come through, the current will come through, and the current will meet up again there. And now is the total current altogether. So this is the total current there at that point. At this point again, excuse me, that still remains the total current. And then the total current moves through the 2 ohm resistor. So there we have the total current. And then it goes through all the way, and it picks up another 12 volts altogether. Now, what else do we remember, my dear learners? And we've talked extensively about this. When the current is coming through, and it comes through, no resistors, the resistance of the conductor is negligible. We take it as non-existent or as 0. Then we go there. Some of the current flows through the 5 ohm resistor. Some of the current flows through the 2 ohm resistor. What does that tell me, my dear learners? It tells me that the current has been divided. And I know that definitely, if I were to connect a voltmeter there, right? Let me say I want to call it V1, and this is completely up to me, right? For the purpose of teaching for now, let us say there I connect a voltmeter, I call it V1, and I connect a voltmeter there, and I call it V2. What I simply know is that V1 will be exactly equal to V2. Why? Because resistors in parallel are not equal to, rather they are not potential dividers, they are not voltage dividers. So the voltage there and there is not divided, so it is the same. That is why we say V1 and V2 is the same. What else do I know theoretically? I know that the current through the 2 ohm resistor, remember current we symbolize it by the symbol I, so the current through the 2 ohm resistor will be greater than the current through the 5 ohm resistor. How do I know that, my dear learners? Let's write it nicely there for you. There we go. Right. The current through the 2 ohm resistor will be greater than the current through the 5 ohm resistor. Why are we saying the current there will be greater than the current there? It is because if the resistance is low and the potential difference is the same, then current is going to increase, or it will be more. If you look at the 5 ohm resistor, if the resistance is high and the potential difference is the same, meaning it's kept constant, then the current on the 5 ohm resistor is going to be low. What else do I know theoretically? I know that the total current is going to be made up of the current that flows right. It will be made up of the current that flows through the 2 ohm resistor plus the current that flows through the 5 ohm resistor. In other words, this was the total current. So when the current divides, all of that, the current that went into that pathway through the 5 ohm resistor and the current that went through the 2 ohm resistor, together adding them will give me the total current altogether. Right. So the total current is the one that is going to be made up of the 2 ohm resistor and the 5 ohm resistors that are connected in parallel, these ones. Now we are required to get the total resistance of the circuit, and I'm sure you are thinking to me, Menier, the total resistance is made up of the resistor in series plus the resistors that are in parallel. Why? Because there we have a resistor that is in series plus the resistors that are in parallel. So we are thinking that, okay, the resistor in series is 2 ohms plus we want the resistor in parallel. Now to get the resistance in parallel, we have to go and calculate it first. So we will say 1 over Rp is equal to 1 over R1 plus 1 over R2 plus 1 over R2. Then we say 1 over Rp is going to be equal to 1 over 2. If we just take this to be R1, it will be 1 over 2 plus, if we take this one to be 5 ohms, rather to be R2, then it will be 1 over 5. Then if you do 1 over Rp with your calculator, it will give you, just quickly go into my calculator. Right, it will give me 7 over 10. But remember, my dear learners, we are not looking for 1 over Rp. We are looking for Rp. So if I want Rp, it means I must take the reciprocal on the left. So Rp divided by 1 is equal to what I did on the left, I must also do on the right. So I will also take the reciprocal on the right. So it will be 10 over 7. Then RP over 1, we definitely know that it will give us RP. And then we say 10, we divide that by 7, and it gives me 1,43 ohms. So I know the value of RP. So the question wanted the total resistance. And that is why we said, okay, the total resistance will be given by this resistor that is in series plus these resistors that are in parallel. So I need to then get the total resistance by adding the resistance in series plus adding the resistance in parallel. And therefore, the resistor that is in series, we agree that it's 2, and R parallel, I calculated it there and I got 1,43 ohms. So this is going to be plus 1,43. And in totality, obviously now my dear learners, when you write it, it will go down altogether. So we are going to say, just do this for you. There we go. Right, from there we will say, okay, then R total is equal to 3,43 ohms. Are we together? So we added the resistor that is in series plus the R parallel that we calculated, and we find that our total resistance is definitely giving us 3,43 ohms. Are we clear? And most likely, remember, we didn't give you the value for R parallel, and that is why you had to show us the calculation. So we'll give you a mark somewhere there, and then we'll also give you a mark for the addition of R series to R parallel, and we'll also give you a mark for the final answer. Remember, my dear learners, if you did not show me how you calculated R parallel, and now you substitute there, and perhaps you substitute the wrong value, there is no way that I can give you marks there, because I don't know where you got the R parallel. You didn't show the calculations. But if you got the R parallel wrong and you substituted there, you will get a mark for substitution, because we are crediting the fact that you are able to work out that the total resistance of this circuit is going to be made up of the resistor that is in series plus the resistors that are in parallel. And then you will forfeit the last mark. So it is very critical that anything that we did not give you a value for, you have to show us the calculations. Right. We move to the next question. The 5 ohm resistor is replaced with a 6 ohm resistor. How will this change influence the following? Right only increases, decreases, or remains the same. So there you've been given an instruction to write down either or perhaps only increases, decreases, or remains the same. It means you can't give us an explanation. How is that going to affect the total resistance of the circuit? Now, if I wanted to find out how it will affect the resistance of the circuit, basically they're saying to me, this is no longer 5 ohms, and let's say it's being changed to 6 ohms. If you change this to 6 ohms, then this RP is going to increase altogether. The value of RP is going to increase. Why is it going to increase? Because now, if you change the 5 ohm to 6 ohm, it means when you go and calculate RP, you would say 1 over RP is 1 over R1 plus 1 over R2. Then it will be 1 over 2 plus 1 over 6. Altogether, my dear learners. And then you perform your mathematics there. Eventually, the value of Rp will be a value that is greater than 1,43 ohms. And now, if now the value of Rp increases and you add 2 plus a value that is greater than 1,43, it means the total resistance will now be greater than 3,43. So our answer there, my dear learners, it's simply increases altogether. Our answer there, it's simply increases. And you see there, very lenient with the marks, you are getting 2 marks. Then, the potential difference over the parallel combination. Now, it is very clear. If along the parallel combination, the total resistance increases, right? Remember, R parallel is going to increase if this is now 6 ohms and not 5 ohms anymore. It means the total resistance across the parallel combination has increased. And if it has definitely increased, then the opposition to the flow of current is going to increase. And if the opposition to the flow of current increases, then it means you will need more electrical energy to overcome that resistance in the parallel combination because you have increased R parallel. So, in a nutshell, when R parallel increases, it simply means the resistance of the parallel combination increases. And if the resistance of the parallel combination increases, then you will require more electrical energy to overcome that opposition to the flow of current, to overcome that resistance that has increased. And therefore, more volts are going to be required. So our answer there is also going to be increases. Are we together? That is the first one. Okay, and there is no resonance that is required, but I have already done that for you. Then 7.3, which is the last question here, it says, calculate the cost to run a washing machine of 230 volts with a current of 20 amperes for 1 hour if the price of electricity is 0.85 rands per kilowatt hour. And we know 0.85 rands simply means 85 cents altogether per kilowatt hour. Now, this is what I want you to remember. We have two different costs, and I told you this yesterday. We have a cost for usage, to say how much in rands or in cents did it cost you to use a certain appliance. But we also have the cost per kilowatt hour. And if you check here, the cost per kilowatt hour is given. It is 0.85 rands, which basically amounts to 85 cents per kilowatt hour. So this is the cost per kilowatt hour when you buy your electricity. So we are not asking you to calculate the cost per kilowatt hour. We want to know the cost of using that machine. Basically, we want the amount in rands. And we don't give you a formula in the formula sheet for this one. So you must know that the cost of usage, remember, I want the cost of usage here. I don't want the cost per kilowatt hour. And this is as simple as I can do it for you. The cost of usage is going to be, remember, if you want to know how much it will cost you to use that, firstly, you must know the rate, ne? You must know the rate per kilowatt hour. So you must know the rate for kilowatt hour, meaning how much does it cost per kilowatt hour. So there is given the price. And you must multiply that by the power rating of the appliance. And then you must multiply that by the time you use that particular appliance altogether. When you know all of that, my dear learners, then you will be able to calculate the cost of usage, and check there, it's 5 marks. Very easy calculation, right? So we have seen the rate per kilowatt hour. And you know what? What I'll simply do for you, remember, we are not required to show the units, but I just want to show you how these units actually cancel. So there we have the rate per kilowatt hour. We know it's 0.85. And remember what per kilowatt hour means. It means 0.85 dot kilowatt hour to the power of -1. We'll multiply that by the power rating. And do we have the power rating? No, we don't. So we need to calculate the power rating. But do we have the time? Yes. And the time, they told me that we'll be running that washing machine for 1 hour. So it will simply be 1H. So I can see there that the only thing that I'm left with is to give you the power rating, or rather to calculate the power rating. Then I will be able to get the cost of usage, the cost of running that machine. So I just want to emphasize this again. We want the price of the cost of usage, and we've been given the rate per kilowatt hour, how much it costs per kilowatt hour. So in writing per kilowatt hour, my dear learners, this statement there, putting it simply in units, it's R 0.85 dot kilowatt hour -1, because -1 means per. So I can see that I am left with just calculating the power rating, and I know that the value for the voltage, it's 230. The current is given there as 20 amperes. So what can I do there to get the power? We'll use the first equation, which you are familiar with by now. We'll use this one, my dear learners. There it is. P is equal to VI. Then for V, okay, P is equal to VI. And then the value of V is 230. And the value of I, which is the current there of 20 amperes, it will be 20. We do our maths. 230 times 20 gives me 4,600 watts. Now, can I go and substitute 4,600 watts? And my answer is no, I can't. Why? Because there I'm dealing with kilowatts. So this watts has to be converted to kilowatts altogether. And then to convert it to kilowatts, I know that I will take the 4,600 watts and I will divide it by 1,000. And if you divide it by 1,000, Right. Without going to the calculator, I am more certain that it will give me 4,6 kilowatts. Altogether, my dear learners. Right, so I'm expecting it to give me 4,6 kilowatts. Then I know the power rating, then I will go there and I will substitute the 4,6 kilowatts. Then if you do your mathematics, we will say, okay, 0.85 multiplied by 4,6 multiplied by 1 gives me 3.91. And 3.91, we know it is rands, so the cost there, it will be 3.91 cents altogether. And how we would normally mark this, my dear learners, is we expect you to get the power rating, so we'll give you a mark there. We'll most certainly give you a mark for the formula. We'll give you a mark for your substitution, right? Perhaps 2 there, and obviously the final mark. So that will be 5 marks altogether. So this is how you should calculate it. And remember, we don't give you a formula. Some of you, you might be familiar with this formula that talks about E is equal to PT, right? You can still use that. This one requires multi-step, and hence I am not really talking about it for now, and we don't give you in the formula sheet. So remember that. Can you see that kilowatt hour -1? I multiplied with kilowatt times hour, which is a kilowatt hour. It means that I have a kilowatt hour -1 with a kilowatt hour +1, which gives me 1. And then the kilowatt hours go, and I'm going to be left with rands. Then we go to this question there, where Lindy investigates the relationship between the current and the energy transferred by a resistor X. So there's a resistor X there, and Lindy is simply trying to find out what is the relationship between the current as well as the energy transferred. Meaning, how does the current moving through the resistor X affects the energy that is transferred by that particular resistor? And this resistor is immersed, in other words, it is dipped in water in an insulated calorimeter. Right, the calorimeter is basically that jar there that you are looking at. She applies constant current of 1 ampere, 2 amperes, 3 amperes, and 4 amperes, each for a period of 5 minutes. So she's basically changing the current that flows through this resistor. So the first time it was 1 ampere, then 2 amperes, then 3 amperes, then 4 amperes. And every time when she does that, she is applying that current for a period of 5 minutes. She uses a thermometer to measure the rise in temperature corresponding to each of the applied events. So she'll measure the temperature there. The mass of the water is kept constant throughout the experiment. The diagram below shows the setup of the apparatus. So there she has a thermometer to measure the temperature corresponding to each current that is applied, meaning in the first experiment when she does the current of 1 ampere flowing through the resistor, then in 2 amperes and so on. And there we have our resistor X, we have our ammeter, our cells, which forms a battery, and our variable resistor. So basically there we have a circuit. Then the energy W that is transferred by resistor X was calculated in each experiment, assuming 100% efficiency, assuming that the current is always 1 ampere in a different experiment, 2 ampere, 3 amperes, 4 amperes, and also that this resistor X is working optimally. The values are presented in a table. Now, there I have current. We know the symbol of current is I. It's measured in amperes. So this is the first experiment with 1 ampere, 2 amperes, 3 amperes, 4 amperes. And there we have current squared. So if it's current squared, it means it's I squared. So the unit will also be amperes squared. So this is simply the value of I and they square it. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. And then the energy, which is represented by W, and remember energy is measured in joules. Transferred by resistor X in joules. Definitely there, we know the joules are a capital letter J. Right, so it is given there. Then we are required to use a suitable scale to draw a graph with energy transferred, and it must go on the vertical axis, the dependent axis, and current squared. This should actually be there on top with current squared. On the horizontal, which is the independent axis. On the graph paper provided, plot the points and sketch a straight line graph. Label your graph clearly. Right, we're almost done. So firstly, a graph must have a title. It must have a heading. So it will be a graph of, and you know, we will start with what goes on the y-axis versus what goes on the x-axis. And we were told that the energy transferred must go on the y-axis. So this is a graph of energy transferred versus so this is a graph of energy transferred versus, we've been asked there to draw that of energy transferred and current squared. So this will be I rather versus current squared. Right. So there, my dear learners, is the title. So when you give the title, you don't have to give the unit of the variables. So our variables there are energy transferred, and the other variable is current squared. Then I will draw my axis. Right? Then we note on the y-axis, it must be energy transferred. And my dear learners, I prefer to write it in full. Right? So this is energy transferred. And remember, you show the variable and in brackets, you write the units. So it is measured in joules, capital letter J. We get a mark. Again, there we have on the x-axis, we are dealing with current squared. Our variable there, it's current squared. Remember, they didn't say current, they said current squared. And if it is current squared, it means it will be measured in amperes squared. So you show the variable and the units. So we get another mark there. So a mark for the heading, a mark for labeling the dependent variable and the units, and a mark for labeling the independent variable, with the units altogether. Sometimes, my dear learners, it could be 1 mark for both axes named and labeled correctly. So if one of the two is incorrect, then you forfeit marks, even if one is correct. Then we must plot. I can see that I have for energy, I have 600, I have 2,400, I have 5,400, and I have 9,600. So what I can do is I can actually scale this. Now, normally you would get a normal graph in blocks there. So let us assume that each block represents 2,000. So it means from there to there, it will be 2,000. So from there to there, it will be another 2,000. So it will take this to 4,000. From there to there, it's another 2,000. So it will be 6,000. From there to there, another 2,000. It will be 8,000. From there to there, it's another 2,000. So this is going to be 10,000. And I'm happy with that because our last value ends at 9,600. And then we come here, right? Current squared, I have 14916. So I can actually say, okay, let from this point to that point to be 4. That point to that point, same size, I will make it 8. That means to the next block. Then to the next block of the same size, I will have 12. Same block, same size again, I will have 16. So I'm happy with that. Now remember, my dear learners, per block, you actually get 10 lines, right? You get 10 lines, you get 10 lines. You get 10 lines there altogether, right? So just to make it neater for us, if you want to know how much each line means, the fact that you know that the entire block is 2,000 and you have 10 lines. If you share the 2,000 amongst 10 lines, it means one line will be 200. So if one line is 200, then when I want to plot, I'm going to say, okay, I have 600 and one line is 200, right? Then it means I'm going to plot on the third line. I said the entire block of 10 lines is 2,000. So if you want to know the individual lines, you take 2,000, you divide it by the 10 lines. So each line will get 200. So if each line is 200, then to get to 600, you must go to the third line, which could be somewhere there. And that is definitely something like 600. And what do we know? 600 for energy, 1 ampere squared. So if this is 4, you will still do the same thing. You will take the 4, which represents a block, you will divide it by 10 altogether. So each line will be 0.4. So if each line is 0.4, then to get to 1, it will be the first line 0.4, the second line 0.8. Just between the second and the third line, you will have 1. So let us assume that 1 is there. So you check where 601 meet. 1, 600, so they meet somewhere there. Remember, my dear learners, mine is not well scaled. And then the next point, it's 4 and 2,400. So I have 4, there I have 2,000. Remember, each line represents 200. So To get to 2,500, I'll go to the first line, which will be 2.2, the next line, which will be 2.4. So it will be somewhere there altogether. Then the next one, it's 9 and 5,400. So to get to 9, remember for this one, each line is 0.4. So I'll go to the first one, it will be 8.4. The second line, 8.8. The third line, it's actually 9.2. So it must be somewhere between the second and the third. So let's assume that it's there and it goes with 5,400. Right. So it will be 4.2 each line, 4.6, 4.4, 4.6, 4.8. 5,000, 5.2, 5.4, which could be somewhere there. Right? And then for 16, I have 9,600. You still do the same thing, my dear learners. It will be on the 8th line, just before you get to 2,000. So 16 and 9,600, it will be somewhere there. Right? And then you draw your line. And it must be a best fit. Perhaps if I were accurate, the dots would connect, but to draw a best fit straight line, I will do something like this altogether. So it's not entirely straight, but more or less works. Straight, a best fit simply accommodates all the points to be closer to the line. So you will get a mark for scaling. You will get a mark for at least the first 2 points plotted correctly and another mark. So be able to do that altogether. Then almost the end. Describe in words the relationship between current squared and the energy transferred by the resistor as reflected by the graph. Now, definitely we know if there is no current flowing through, the energy that is dissipated is also going to be zero. So it's more likely that this graph is definitely cutting through the origin. So the relationship is direct proportionality altogether. So they said we must actually describe it. So what we are going to say is current squared. Remember, they didn't say with current, they said with current squared. Current squared is directly proportional to energy transferred. There we go. And that is definitely 2 marks. Current squared is directly proportional to energy transferred, definitely by the resistor altogether, and you will get 2 marks. Remember, they said we must describe in words. So description means you must explain. So we can't just say directly proportional. We need to state it altogether. We give the variables, which is current squared and energy transferred, and we give the relationship between the two. And to conclude, we are required to calculate the resistance of the resistor Lindy used in her investigation. Now, we have quite a number of formulas. For this one, my dear learners, when you go to your formula sheet, there's a formula there for W. Remember, W is the energy transferred. And one of the formulas simply says W is I squared R multiplied by delta T, which is this formula here, altogether. And amongst others, there's more formulas. So depending on what is been given, you will check which formula is suitable. So what is suitable for us now? It's this formula. Then we know that there is 100% efficiency. So any of these values or any of these experiments is going to work for us. So we can choose any. Let us choose perhaps for experiment number 2. We know that W is the energy transferred, and the energy transferred in this case is definitely 2,400. So we have 2,400 current squared there. Remember, this is current squared. It's already squared. So it will be 4 altogether. Or you could have chosen current, which is 2, but then you would have to square it. Multiplied by the resistance. And our resistance is what we are looking for. Multiplied by delta T. Now remember, they said she applied the current to the resistor for 5 minutes. And we know in our formula, my dear learners, we cannot use that time in minutes. It has to be converted to seconds altogether. So how do we do that? We know that in 1 minute, we actually have 60 seconds. So in 5 minutes, we have X number of seconds. Then we cross multiply. So it will be 1 minute multiplied by X seconds. And I know it's easy, my dear learners. And it will be 5 minutes multiplied by 60 seconds. And to get the number of seconds, it will definitely give us 300 seconds. Basically, if 1 minute it's 60 seconds, 5 minutes, it will be 5 times 60 seconds. It will be 60 seconds, but 5 of them. And that is why we say it gives us 300 seconds. And we'll multiply there by 300. And to get the value of R, we know we must take the 2,400 and we must divide it by 1,200, and we are going to get that the resistance gives us 2 ohms. Altogether, my dear learners. Right, remember, this side will have 2,400. On the right-hand side, it will be 4 times R times 300. It will give you 1,200 R. And you will divide both sides by 1,200. And then on the right, you'll be left with R. And then on the left, 2,400 divided by 1,200 gives you that R is 2 ohms altogether. So quite an easy calculation. So I hope that you really understood what we talked about, and we have definitely covered everything on this topic as per the examination guidelines. Remember, this topic, it's plus minus 15 marks in paper 1, and you can really do well. So be able to deal with your series circuits, your parallel circuits, combination of series and parallel circuits, be able to deal with power calculations, be able to deal with the cost of electricity, and be able to deal with the heat that is produced or the heat that is dissipated altogether. Also be able to differentiate between ohmic conductors and non-ohmic conductors. And in a nutshell, practice and practice and practice. Send me your questions to STEM Digital School at africateengigs.co.za. There it is on your screens. Use it. And That will help us tomorrow so that I'm able to answer any questions that you ask me during our question and answer session. I hope you enjoyed the lesson, and I will see you tomorrow between 12:30 and 2:30. Thank you and enjoy the rest of the evening. Goodbye.